Billions of light years away, a cosmic corpse spins faster than a kitchen blender. This is a neutron star, the crushed core of a dead giant, and we are finding them in the farthest reaches of space. We are about to journey across the cosmos to uncover 25 staggering truths about these distant relics. You will discover how they warp the fabric of reality, forge the gold in your jewelry, and serve as perfect clocks ticking from the dawn of time. What secrets about the universe's violent youth are locked inside these ancient objects? How can something with the mass of a sun be smaller than a city? By the end, you will understand why these pinpoint beacons are the universe's ultimate physics laboratories. What do you think is the most extreme thing an object in space can do? To grasp the first fact, we must first stretch our minds around the word distant. In our daily lives, distant might mean a faraway city or another continent. But here, distant means something almost incomprehensible. We are finding neutron stars not just in our own Milky Way, but in galaxies so far away that their light has been traveling for billions of years just to reach our telescopes. Think of the Andromeda Galaxy, our nearest large galactic neighbor. Its light takes about 2.5 million years to get here. Now multiply that journey by 1,000. The neutron stars we are discussing are often 10,000 times farther than that. When we detect one of these objects, say, 12 billion light years away, we are not seeing it as it is today. We are seeing it as it was 12 billion years ago, when the universe itself was in its wild, formative youth. This makes every distant neutron star a fossil, a preserved snapshot of a moment when the cosmos was assembling its first generations of stars and galaxies. By studying them, astronomers are not just looking across space, they are peering back through time, reading a chapter from the universe's own ancient history book, written in the language of spinning, magnetic corpses. Their incredible journey begins with a violent end. To become a neutron star, a star must first die in the most spectacular fashion possible. Picture a star many times more massive than our own sun. For millions of years, it burns brilliantly, fusing hydrogen into helium in its core, then helium into carbon, and so on, like a cosmic onion with heavier elements layered at its heart. This process cannot last forever. Eventually, the star builds an iron core. Iron is a dead end for fusion. It consumes energy instead of releasing it. With its internal furnace suddenly shut off, the star has no outward pressure to fight the relentless inward crush of its own immense gravity. In a fraction of a second, the core collapses. It falls inward at nearly a quarter the speed of light. The outer layers of the star plummet after it, only to smash into the now unimaginably dense core and rebound in a cataclysmic shockwave. This is a core collapse supernova. The resulting explosion outshines an entire galaxy for a brief moment, blasting the star's enriched outer layers into space, seeding the cosmos with the elements necessary for planets and life. All that remains is the collapsed core, crushed by gravity into a sphere just about 12 miles across, yet containing more mass than our sun. This is the newborn neutron star. Now consider the most distant ones we detect. Their light has traveled for over 12 billion years. That means we are witnessing the aftermath of supernova that detonated when the universe was less than 2 billion years old. These neutron stars are the compact graves of the very first generation of giant stars to live fast and die young. They are the ancient, dense fossils from the universe's most foundational explosions, the original forges that began the long process of enriching a once-empty cosmos with the building blocks of everything we see today. The sheer violence of that birth leaves behind an object of almost impossible density. This is the third and perhaps most mind-bending fact about these distant beacons. A single teaspoon of material scooped from the surface of a neutron star would weigh around 1 billion tons. To put that into perspective, that tiny spoonful would have a mass equal to every human being on Earth combined, or the weight of Mount Everest. This staggering density is not just a fun fact, It is the core reality that defines everything strange about these objects. The gravity on the surface of a neutron star is about 100 billion times stronger than the gravity we feel on Earth. This force is so unimaginably powerful that it does something profound to the very structure of matter. It completely overcomes the forces that give atoms their spacious structure. In normal matter, atoms are mostly empty space, with tiny electrons whizzing around a dense nucleus, but under the neutron star's crushing gravity, that empty space is eliminated. The atoms are smashed together so violently that the electrons are forced into the atomic nuclei. There, they merge with protons to form more neutrons. The entire star, aside from a possible thin, solid crust, becomes a sea of neutrons packed shoulder to shoulder, a substance physicists call neutronium. It is essentially one giant atomic nucleus, the size of a city. This is matter in a state that does not and cannot exist anywhere on Earth. Our most powerful particle colliders can only create these conditions for a fleeting fraction of a second in a space smaller than an atom. A distant neutron star, however, is a permanent natural laboratory where this exotic state of matter exists on a colossal scale. By studying the light and spin of these faraway objects, astronomers are conducting physics experiments across billions of light years, testing the very laws that govern the fundamental forces of nature under the most extreme pressure the universe can create. This incomprehensible density forces them to obey one of physics' most fundamental rules, the conservation of angular momentum. Picture a figure skater pulling their arms in during a spin, their rotation speeding up dramatically as their mass moves closer to the center. Now apply that to a dying star. A giant star, even as it slowly rotates, possesses an immense amount of spin energy spread across its vast body. When its core collapses from a sphere hundreds of thousands of miles wide down to a city just 12 miles across, that spin energy is concentrated into an impossibly tiny package. The result is a newborn neutron star spinning at a blistering, almost unfathomable rate. Some have been clocked rotating hundreds of times every single second. The current record holder, a neutron star named PSRJ 1748-2446d, spins over 700 times per second. At that speed, its surface at the equator is moving at about 1/4 the speed of light. This is not just a curiosity, it is the engine that creates one of the universe's most reliable beacons, the pulsar. A pulsar is a neutron star with a powerful magnetic field that is tilted relative to its spin axis. This misalignment acts like a cosmic lighthouse. Beams of intense radiation, from radio waves to gamma rays, shoot out from the magnetic poles. As the star spins, these beams sweep across space. If one of those beams happens to cross the path of Earth, our telescopes detect a regular pulse of energy with every rotation, a perfect metronomic tick echoing across the light years. For the most distant neutron stars, detecting and measuring this spin is a monumental challenge, but it holds priceless information. The spin rate of a pulsar is a fossil record of its violent birth. A faster spin tells astronomers that the progenitor star collapsed more symmetrically, transferring its rotational energy with ruthless efficiency. A slower initial spin might hint at a more chaotic explosion. By finding and timing the pulses from these ancient faraway lighthouses, we are not just noting a number, we are reading the spin signature of supernova that detonated when the universe was in its infancy, understanding the precise dynamics of cosmic deaths that happened before our solar system even existed. But the spin is only half the story of a pulsar's power. That same stellar collapse that creates a dizzying rotation also forges a magnetic field of pure, distilled ferocity. A typical neutron star possesses a magnetic field 1,000,000,000,000 times stronger than Earth's protective magnetic bubble. To grasp that scale, think of a simple refrigerator magnet. Its field is strong enough to hold up a piece of paper. Earth's field, which guides compass needles and shields us from solar radiation, is about 1 Gauss in strength. A neutron star's field can measure 1 quadrillion Gauss. That is a 1 followed by 15 zeros. This is not merely a strong magnet, it is a force that redefines the behavior of matter and energy in its vicinity. The magnetic field is so powerful it can literally stretch and squeeze atoms into thin, needle-like shapes. It can lock radiation in place, creating an atmosphere not of gas, but of a seething, constrained plasma. The most extreme members of this family are called magnetars. These are neutron stars where the magnetic field is 1,000 times stronger still, pushing the very limits of physics. Such a field stores an astronomical amount of energy, and it is not always stable. Occasionally, the crust of the magnetar, a crystalline lattice under unimaginable strain, will crack. This is a starquake. When it happens, the magnetic field lines snap and reconnect, unleashing a catastrophic blast of energy in a fraction of a second. In that instant, a magnetar can release more energy than our Sun will emit in 100,000 years. The flash is so intense it can temporarily outshine every other gamma-ray source in the entire observable universe, including the combined light of billions of galaxies. For astronomers seeking the most distant neutron stars, these colossal tantrums are a gift. A single brilliant gamma-ray flare detected from a galaxy 12 billion light-years away is a clear, unmistakable signature. It tells us that in that far-off island of stars, a magnetar just had a catastrophic hiccup. We are not seeing the steady pulse of a lighthouse, but the violent scream of a magnetic monster, a beacon of pure extremity that cuts across cosmic distances to announce its impossible existence. These monstrous magnetic flares and steady cosmic ticks are how we find needles in the deepest haystacks of the universe. Astronomers have 3 primary methods for detecting these distant neutron stars, each a testament to both the star's extreme nature and our own technological ingenuity. The first and most iconic method is catching the pulse of a pulsar. As that rapidly spinning neutron star sweeps its lighthouse beam across the cosmos, telescopes on Earth can pick up the rhythmic flashes. For the most distant ones, these pulses are often not in radio waves, which can be scattered and absorbed over billions of light-years, but in higher energy X-rays. Specialized space telescopes like Chandra or XMM Newton act as cosmic metronomes, timing these faint, precise ticks that have crossed the void for eons. Each pulse is a time capsule, its regularity allowing scientists to measure the star's spin, its slowdown, and even deduce the presence of planets orbiting it, all from an unthinkable distance. The second method is the opposite of regularity. It is catching chaos. For magnetars, astronomers watch for their sudden, catastrophic starquakes. When the crust cracks and the magnetic field reconfigured, it unleashes a torrent of gamma rays, the most energetic form of light. Satellites like the Fermi Gamma Ray Space Telescope are on constant patrol for these brief, blinding flashes. Detecting one from a galaxy 12 billion light-years away is like seeing a camera flash go off on a distant mountain during a starry night, a fleeting but unmistakable sign of violent activity. That single burst, lasting perhaps 1/10 of a second, contains enough information to confirm the existence and approximate location of one of the most magnetic objects in creation, a beacon of pure extremity. The third method involves looking for a cosmic vampire. Some neutron stars are not alone. They exist in a binary system with a companion star. If the stars are close enough, the neutron star's immense gravity can begin to steal or accrete gas from its partner. This stolen material does not fall gently. It spirals in at nearly the speed of light, forming a searing hot disk around the neutron star. The friction and impact heat this material to temperatures of millions of degrees, causing it to glow brilliantly in X-rays. These X-ray binaries shine with a distinctive, flickering signature that space telescopes can identify. By studying the properties of that X-ray light, astronomers can weigh the invisible neutron star, measure its rotation, and understand how it feeds. Finding such a system at a colossal distance tells a story of a binary partnership that has survived a supernova explosion and now persists, one star slowly being consumed by its undead companion, in a galaxy far, far away. Each detection method, whether it is a steady pulse, a violent burst, or the glow of stolen fire, is a triumph of persistence, turning faint whispers from the edge of time into profound discoveries about the universe's most compact mysteries. This relentless hunt for distant ticks and flashes has led to some truly breathtaking discoveries. One such record holder, a pulsar known by the catalog number PSRJ0901-4046, makes its home not in our Milky Way, but in a distant galaxy called NGC 300. While not the absolute farthest ever detected, its location over 6 million light-years away places it firmly in another galactic neighborhood, and its story perfectly illustrates the monumental challenge of finding these objects. Its pulses of radio waves, born from a magnetic field of staggering power, embark on an epic journey. For 6 million years, that rhythmic signal travels through the expanding fabric of space itself. This expansion does something subtle but profound. It stretches the very wavelength of the light, shifting it toward the red end of the spectrum. By the time those faint whispers finally reach our most sensitive radio telescopes, like the Mir Kennedy Array in South Africa, they are incredibly weak and significantly redshifted. Detecting this pulsar was not a matter of simply pointing a telescope. It was an act of exquisite patience and computational power. Astronomers had to collect hours of data, then use sophisticated algorithms to search for a repeating pattern buried under cosmic static. Finding its steady pulse was like identifying the heartbeat of a specific insect in a roaring stadium, while listening from a city miles away. Its discovery is a testament to how far our technology has come, proving that we can now tune into the metronomic ticks of cosmic lighthouses shining from galaxies beyond our own. And the hunt continues, pushing instruments to their limits, searching for even fainter pulses from neutron stars born when the universe was half its current age, their signals stretched and faded into near silence by an expanding cosmos. This incredible regularity transforms a pulsar from a simple beacon into something far more profound, a perfect cosmic clock. The spin of a millisecond pulsar, one that rotates hundreds of times per second, is so stable that it can rival the precision of the best atomic clocks we build here on Earth. Its pulse arrives with a predictability measured in billionths of a second over decades. This is not just a curiosity, it is a tool of staggering power for fundamental physics. Astronomers realized that by carefully monitoring an array of these celestial metronomes scattered across our galaxy, they could create a galaxy-sized observatory for something invisible, gravitational waves. This network is called a pulsar timing array. Here is how it works. Imagine you have a dozen of the most perfect clocks imaginable, each ticking away in different parts of the sky. Now imagine a ripple in spacetime itself, a low-frequency gravitational wave from a distant collision of supermassive black holes, passing through our region of the galaxy. As that ripple washes over Earth, it minutely stretches and compresses the space between us and each pulsar. This subtle distortion causes the arrival time of the pulses to shift by a tiny, almost imperceptible amount. No single shift is convincing, but by comparing the precise timing of all the pulsars in the array over many years, a correlated pattern emerges from the noise. It is like trying to detect a gentle swell in the ocean by watching how a fleet of buoys rises and falls in unison. In June 2023, several international collaborations announced they had found the first compelling evidence for this gravitational wave background, a cosmic hum likely from countless merging giants across the universe, all detected by listening to the synchronized ticks of dead stars. While the current arrays rely on pulsars within our Milky Way for their stability, the future holds an even grander vision. Finding exceptionally stable millisecond pulsars in distant galaxies would extend this cosmic GPS network across the universe. Each distant ancient clock would become a new anchor point, allowing us to triangulate gravitational wave sources with far greater precision and listen to the deepest, lowest notes of the cosmic symphony, frequencies too long for any other observatory to hear. That perfect tick from a cosmic clock is more than just a signal, it is a probe. It travels through the very fabric of the universe, a fabric that is not static but dynamic, warped and curved by mass and energy. This brings us to the ninth staggering fact about these distant objects. A neutron star does not just sit in space, it actively bends the geometry of reality around it. Its immense mass, often 1.5 times that of our Sun, is compressed into a sphere you could drive across in 20 minutes. This creates a gravitational field so intense that it significantly curves spacetime, the four-dimensional continuum that forms the stage for everything that happens in the cosmos. According to Einstein's theory of general relativity, mass tells spacetime how to curve, and curved spacetime tells mass how to move. A neutron star is a master sculptor of this cosmic geometry. This curvature has direct, observable effects. First, it affects the star's own light. Radiation struggling to climb out of the deep gravitational well of a neutron star loses energy in a process called gravitational redshift. The light we finally detect is slightly redder, or lower in energy, than when it was emitted. For the most precise pulsars, astronomers must account for this redshift to measure their true spin rates accurately. Second, this warping dictates the motion of anything nearby. If a neutron star has a companion star, that partner will orbit not in a simple ellipse as described by Newton, but in a complex, precessing path dictated by the curved spacetime around its dense partner. The orbit itself becomes a map of the warped geometry. The most famous proof of this came not from a distant star, but from a binary pulsar discovered in our own galaxy in 1974, known as the Hulse-Taylor pulsar. This system consists of two neutron stars orbiting each other rapidly. By meticulously timing the pulses from one of them for decades, astronomers Russell Hulse and Joseph Taylor observed that the orbit was decaying. The two stars were slowly, inexorably spiraling inward. The energy they were losing matched the predictions of general relativity perfectly. It was being carried away by ripples in spacetime itself, gravitational waves. This was the first indirect, but spectacularly convincing, evidence for gravitational waves, a discovery that earned them the Nobel Prize in Physics in 1993. Now imagine finding a similar binary pulsar system not in our Milky Way, but in a galaxy 10 billion light-years away. Observing the orbital decay of such an ancient pair would be like running Einstein's equations on a cosmic timescale. It would test whether the fundamental strength of gravity, described by general relativity, has remained constant over nearly the entire history of the universe. A distant orbiting neutron star is not just a pair of dense objects. It is a natural laboratory for the most profound laws of physics, operating on a stage billions of years old. The gravitational waltz of a binary system can sometimes turn into a slow, cosmic murder. Among the most bizarre inhabitants of the neutron star, zoo, are the so-called spider pulsars. These are millisecond pulsars locked in a tight, deadly embrace with a stellar companion, and they are named for their gruesome feeding habits. The most extreme are the black widows. In these systems, the pulsar is a rapidly spinning monster. Its intense radiation and powerful wind of high-energy particles relentlessly battering its much smaller partner. This companion is often a brown dwarf or a planet-sized object, utterly dwarfed by its dense neighbor. The pulsar's energy output is so fierce that it is literally cooking and evaporating the companion star, stripping away its outer layers atom by atom. Over millions of years, this process will completely disintegrate the smaller star, leaving the pulsar alone once more, a solitary killer spinning in the dark. Then there are the redbacks, named for another notorious spider. These feature a pulsar with a larger, low-mass stellar companion, perhaps 1/10 the mass of our Sun. The companion is puffed up and bloated, filling its gravitational lobe, and the pulsar's wind continuously blasts it, creating a turbulent shroud of gas that often eclipses the pulsar's radio signals from our view. These systems are messy, violent, and active, with the pulsar occasionally switching between radio bright and radio quiet states as the stellar wind ebbs and flows. Discovering a spider system in a distant galaxy is a monumental find. It tells a vivid story of stellar evolution from the universe's early chapters. It reveals that binary star systems not only survived the catastrophic supernova that created the neutron star, but that they then underwent a long, slow dance of destruction and rebirth. The companion star, in its death throes, actually fuels the pulsar's incredible spin. As material from the evaporating star spirals onto the neutron star, it transfers angular momentum, spinning it up to those dizzying millisecond rates. This is the recycling process, where an old, slowed pulsar is resurrected as a precision cosmic clock by cannibalizing its partner. Finding such a system billions of light years away confirms that this gruesome yet efficient recycling mechanism was already at work in the infant cosmos. It means the universe's first generations of stars were not just isolated giants that lived and died alone, but that complex, interacting partnerships existed, leading to some of the most extreme and precise objects we can observe today. Their gruesome feeding habits are just one part of a grander cosmic cycle, one that transforms them from mere corpses into creators. Beyond their spin and magnetic fury, neutron stars serve as the universe's ultimate factories for the heaviest elements. Every piece of gold jewelry, every platinum ring, and the uranium that powers some of our energy all originated in the most violent events imaginable. The common supernova explosion of a massive star can forge elements up to iron, but to build anything heavier requires an even more extreme environment. This is where the rapid neutron capture process, or the R process, comes in. Picture a nucleus of a lighter element, like iron, caught in a torrent of free neutrons. In the unimaginable heat and density following a neutron star collision, neutrons flood the surrounding debris at an incredible rate. These neutrons slam into the seed nuclei faster than the nucleus can radioactively decay. It's a frantic, chaotic assembly line where a nucleus can gobble up dozens of neutrons in less than a second, bulking up rapidly to become a super heavy, unstable element. That element then undergoes a series of radioactive decays, settling down into stable, precious metals like gold and platinum. For decades, this was a compelling theory, but the proof arrived in a spectacular flash on August 17, 2017. Gravitational wave observatories detected ripples in spacetime from an event dubbed GW170817. Just seconds later, telescopes across the globe swiveled to the same patch of sky and witnessed the aftermath, a kilonova. This was the brilliant, radioactive glow of the material ejected from two colliding neutron stars. The light's signature was unmistakable. It carried the clear fingerprints of newly forged heavy elements, including vast amounts of gold and platinum. In that single event, astronomers estimated that the merger produced perhaps 200 Earth masses of pure gold. Now, consider the most distant neutron stars we detect. When they were born in the early universe, and when they eventually spiraled together in mergers, they performed this alchemy on a cosmic scale. These ancient collisions seeded pristine galaxies with the first atoms of gold, platinum, and other rare Earth elements. The iron in your blood was forged in a supernova, but the gold on your finger was likely born in the catastrophic merger of two neutron stars that occurred billions of years ago in a galaxy far, far away. Every heavy atom in our bodies and our world is a piece of stellar shrapnel from a cosmic cataclysm, and distant neutron stars were the original smiths. That distant kilonova flash was not just a theory anymore, it was a reality witnessed in real time. On August 17, 2017, the universe delivered one of the most profound scientific observations in history. For the first time, humanity saw and heard the same cosmic event. Gravitational wave observatories, LIGO in the United States and Virgo in Italy, detected a distinctive ripple in spacetime. It was not the deep thud of merging black holes they had heard before. This was a higher-pitched chirp lasting about 100 seconds, the clear signature of two incredibly dense objects spiraling together. The data pointed to neutron stars. Crucially, the detectors provided a rough sky location. Within seconds, an alert went out to astronomers worldwide. Telescopes of every kind, from gamma-ray satellites to optical observatories to radio dishes, swiveled to that patch of sky. They found it in a galaxy called NGC 4993, about 130 million light-years away. A new point of light blossomed. This was the kilonova, the radioactive fireball from the merger. For days, it shone with a peculiar, shifting color, from blue to deep red, as heavy elements formed and decayed within it. The analysis was definitive. The light carried the spectral fingerprints of strontium and other R-process elements, proving once and for all that neutron star collisions are cosmic gold factories. This single event, known as GW170817, solved a decades-old mystery. It confirmed that the heaviest atoms in our universe are forged in these violent unions. But its legacy is even greater. It marked the dawn of multi-messenger astronomy, where we no longer just see the cosmos, we can now listen to its ripples and feel its vibrations, opening a completely new window onto the most extreme events in existence. That gold-forging collision reveals a hidden truth about neutron stars. They are not featureless balls of goo. They possess a complex internal architecture, and their outer layer is a marvel of extreme material science. Beneath a thin atmosphere of plasma lies the neutron star's crust, a structure unlike anything found on Earth. This crust is not rock, it is a crystalline lattice of atomic nuclei, but these are nuclei like we have never seen. Under the crushing gravitational pressure, electrons have been forced into the protons, creating a dense soup of neutrons. The atomic nuclei that remain are incredibly neutron-rich, exotic forms of elements like iron that could never be stable in our laboratories. These nuclei are arranged in a rigid, orderly pattern, like a diamond lattice, but they are submerged in a flowing sea of free neutrons that leak out from their cores. This combination creates a material of almost mythical strength. The neutron star crust is the strongest material in the known universe. Physicists calculate its shear strength, its resistance to breaking under stress, to be about 10 billion times greater than that of steel. A cubic centimeter of this crustal material could support a weight equivalent to Mount Everest without deforming. This incredible strength, however, has its limits. The neutron star is spinning with immense kinetic energy, and its powerful magnetic field is locked into this super-strong crust. As the star spins down over millennia, losing rotational energy, its shape must subtly change. The rigid crust resists this change, building up immense strain, like tectonic plates on Earth. Eventually, the strain becomes too great, the crust cracks. This is a starquake. When it happens on a typical pulsar, the sudden shift in the star's moment of inertia causes a tiny but detectable speed up in its spin, a phenomenon astronomers call a glitch. It is as if the spinning figure skater suddenly pulled their arms in a tiny bit more, causing a fractional, unexpected increase in rotation, but on a magnetar, with its unimaginably powerful magnetic field threaded through the crust, a starquake is a cataclysm. The cracking crust releases pent-up energy and causes the magnetic field lines to snap and violently reconnect. This unleashes those colossal gamma-ray flares we can see from across the universe, bursts of energy that briefly outshine everything else. So that distant flash of gamma rays might not just be a magnetic hiccup. It could be the sound of a continent-sized piece of the universe's strongest material suddenly shattering under stress. But what lies beneath that unbreakable crust? As we journey deeper toward the neutron star's heart, The density soars beyond even the realm of rigid lattices. Here, at pressures 100 trillion times greater than Earth's core, matter enters states so bizarre they defy simple description. Physicists theorize that the atomic nuclei, which have already been squeezed into exotic, neutron-rich forms, begin to lose their individual identities entirely. In this transitional layer, a strange competition unfolds. The strong nuclear force, which binds protons and neutrons together, tries to clump matter into larger structures. Meanwhile, the repulsive Coulomb force, the electric repulsion between positively charged protons, tries to keep those structures apart. The result is not a uniform soup, but a cosmic kitchen of deformed, otherworldly shapes. This speculative realm is whimsically known as nuclear pasta. First, nuclei might stretch into long, thin tubes, like strands of spaghetti. Under greater pressure, these tubes could merge into flat sheets resembling lasagna. Deeper still, the sheets might perforate and break into nacai-like blobs, or even form complex, labyrinthine structures akin to a waffle. This is not a culinary fantasy, but a serious theoretical prediction for the behavior of matter under conditions so extreme they can only be modeled on supercomputers. The properties of this nuclear pasta are crucial. It is likely the strongest material in the universe, even surpassing the neutron star crust, potentially forming a rigid framework that supports the star's immense magnetic field. Its strange conductivity influences how heat escapes from the star's fiery interior, dictating its cooling rate over millions of years. Most intriguingly, this exotic layer could vibrate in unique ways. Just as a bell rings with a specific tone when struck, a starquake sending tremors through the nuclear pasta might cause the entire star to oscillate or ring at specific frequencies. These vibrations would be too faint to see with light, but they could ripple outward as gravitational waves. Future observatories, like the planned Laser Interferometer Space Antenna, LISA, might one day be sensitive enough to detect these subtle spacetime ripples from nearby neutron stars. Tuning into that cosmic hum would be like listening to the resonant frequency of a sphere of nuclear spaghetti, giving us our first direct sonic map of matter in its most alien and densely packed form. This descent into the heart of a neutron star leads to the edge of physics itself, and to a staggering possibility. Some of these distant, dense objects might not be neutron stars at all. They could be something far stranger, theoretical entities known as strange stars. The idea pushes our understanding of matter to its absolute limit. We know that inside a neutron star, protons and electrons have been crushed together to form a sea of neutrons. But what if the pressure is so unimaginably great that even the neutrons themselves cannot survive? A neutron is not a fundamental particle. It is made up of three smaller particles called quarks, specifically 2 down quarks and 1 up quark. Theorists propose that under the most extreme gravitational pressures in the universe, the boundary separating individual neutrons could vanish entirely. The entire star might undergo a phase transition, dissolving into a vast, uniform soup of free quarks. This would not be a soup of just any quarks. The intense energy could transform some of the down quarks into a heavier, more exotic variety known as strange quarks. The result would be a new, stable state of matter called strange matter, a plasma of up, down, and strange quarks flowing freely. This substance would be the most perfect fluid in existence, with virtually no internal friction. A star made of this stuff, a strange star, would represent matter in its ultimate, densest possible form. It would be the true endpoint of gravitational collapse, even more extreme than a neutron star. If such an object exists, it would have telltale signatures. Because quark matter can be packed even more tightly than neutron matter, a strange star of the same mass would be slightly smaller. Its surface would be incomprehensibly smooth, possibly just a few miles across, and it would cool in a different way. The most exciting prospect for astronomers is that some of the distant, compact objects we have already detected might, in fact, be these bizarre quark stars. When we measure the size and mass of a particularly small, dense pulsar billions of light years away, and the numbers just do not fit the models for a normal neutron star, it could be the first hint that we are looking at something entirely new. It would mean that in the furnaces of the early universe, conditions were so severe that they did not just crush atoms, they crushed the very building blocks of atomic nuclei, creating islands of primordial quark soup that still drift through the cosmos today. The search for these objects is a search for the absolute limits of reality. A newborn neutron star is a blistering ember, born from a supernova's heart at temperatures exceeding 1 trillion degrees. But even this cosmic furnace cannot stay hot forever. These distant stellar corpses cool down in fascinating and complex ways, their fading warmth telling a silent story about the deepest secrets locked within. The primary battle for heat loss happens on two fronts, the surface and the core. From the surface, energy escapes as thermal photons, the same kind of light that radiates from a hot stove. This creates a detectable X-ray glow, especially in young, isolated neutron stars. But this surface cooling is a slow, inefficient process, like trying to cool a volcano by letting heat escape through a single tiny vent. The real action, the rapid initial cooling, happens deep within the core through a far more exotic mechanism, neutrino emission. Neutrinos are ghostly, nearly massless particles that barely interact with normal matter. They can stream right through the entire star as if it were not even there. In the super-dense heart of a neutron star, several powerful processes can generate a flood of these particles. One is the direct Urca process, where neutrons decay into protons, electrons, and antineutrinos, only for the protons to immediately recapture the electrons, releasing more neutrinos. It is a continuous cycle that drains thermal energy at a phenomenal rate. Other processes, with names like modified Urca and neutron bremsstrahlung, also contribute to this neutrino blizzard. For the first million years or so of a neutron star's life, this internal neutrino wind is the dominant cooling force, carrying away energy at a rate 1,000,000 times faster than the surface photon emission. The star's temperature plummets rapidly during this phase. After this, as the core chills, neutrino production slows, and the slower surface photon cooling takes over for the rest of the star's multi-billion-year life. This timeline, the cooling curve, is not one size fits all. It is a direct fingerprint of the star's internal composition. A star that cools faster than standard models predict might have exotic particles like pions or free quarks in its core, which enhance neutrino production. A star that cools more slowly might have a superfluid core, where neutrons pair up and flow without friction, which actually suppresses some neutrino processes and acts as an insulator. So, by carefully measuring the temperature of a neutron star, astronomers can, in principle, perform a remote ultrasound of its interior. The challenge with the most distant neutron stars is immense. Their faint X-ray glow is stretched and dimmed by cosmic expansion, but if we could precisely measure the temperature of an ancient, isolated neutron star 12 billion light-years away, we would be reading the cooling signature of an object from the universe's youth. We would learn what its core was made of when galaxies were first assembling, testing whether exotic matter existed in these extreme environments from the very beginning. That faint, fading X-ray whisper is a coded message about the fundamental state of matter under pressures that defy imagination. That fading X-ray glow is our only window onto a landscape of impossible perfection. The surface of a neutron star is not a place you could ever stand, but if you could, you would be greeted by a realm of both unimaginable heat and impossible smoothness. We call this outer layer the photosphere, the region from which most of its detectable light finally escapes. Here, temperatures routinely soar above 1,000,000 degrees and in younger stars can reach tens of millions. This is not the gentle warmth of a summer sun, but a searing, brutal heat that causes the thin plasma of the atmosphere to glow not in visible light, but in high-energy X-rays. To our telescopes, a solitary, cooling neutron star appears as a faint, steady pinprick of X-ray light against the blackness of space. But this light carries a hidden signature of the surface it came from, a surface shaped by a force far more powerful than heat, gravity. The gravity on a neutron star is so overwhelmingly strong that it does something remarkable to its topography. It enforces a near-perfect smoothness. Any potential mountain, any bulge or irregularity on the surface is immediately crushed flat by the star's own weight. The entire object is pulled into a shape as close to a perfect sphere as natural forces can make. Theoretical models suggest that the tallest possible mountains on a neutron star would be no more than a few centimeters tall, perhaps up to the height of a pencil. Over a sphere 12 miles wide, this is an astonishing degree of smoothness. If you scaled a neutron star up to the size of Earth, its entire surface would vary in height by less than 5 meters. This makes it arguably the smoothest known object of its size in the entire universe. This incredible smoothness is not just a curiosity, it directly impacts the light we see. Because the surface is so uniform, the X-rays it emits come from a very well-defined layer. There are no deep valleys or towering peaks to create shadows or complex temperature variations across the disk we observe. This allows astronomers to model the emission more precisely. When they analyze the X-ray spectrum, the detailed breakdown of energy coming from the star, they can use it to estimate the star's temperature and, crucially, its true size. A smoother surface gives a cleaner, more interpretable signal. Discrepancies between the observed X-ray spectrum and the models might hint at a magnetic field distorting the atmosphere, or perhaps the presence of that thin, solid crust beneath the glowing plasma. So, that faint X-ray pinpoint from a distant galaxy is more than just a sign of heat. It is a reflection in a near-perfect cosmic mirror, telling us about the flawless shape sculpted by the most intense gravity we can observe. That near-perfect cosmic mirror might be shrouded by the thinnest veil imaginable, while the neutron star's surface is a searing, smooth layer of degenerate matter. Some of these objects are thought to possess a true atmosphere. But this is no sky like our own. Under a gravitational pull 100 billion times Earth's, any gaseous envelope is compressed into an unimaginably thin skin. We are talking about an atmosphere potentially only a few millimeters thick. Picture the width of a pencil lead, and then imagine that being the entire column of air above you, held down by a force that could crush atoms. This wispy layer, if it exists, would be composed of the lightest elements, likely hydrogen or helium that has settled from the interstellar medium or from the ashes of the supernova. In more exotic cases, the atmosphere might be composed of heavier elements like carbon or oxygen, literally fused on the star's surface by the intense heat and radiation. This millimeter-thin shroud, however tenuous, is a crucial interface between the star's incredible interior and the empty space around it. It is the final filter through which all the star's thermal X-rays must pass before streaming out into the cosmos. And like any filter, it leaves a mark. As the X-ray photons from the hot surface travel through this ultra-dense atmospheric layer, atoms within it can absorb specific wavelengths of light. This creates tiny, dark notches in the star's overall X-ray spectrum, known as absorption lines. Each element absorbs light at a unique fingerprint of wavelengths. For astronomers, detecting these faint absorption lines is like finding a secret signature. It is a direct way to determine the chemical composition of the atmosphere itself. But the story gets even more profound. The immense gravity does not just hold the atmosphere down, it also warps the light escaping from it through gravitational redshift. This stretches the absorption lines, shifting them toward longer, redder wavelengths. The precise amount of this shift is a direct measure of the star's surface gravity. By analyzing the pattern and position of these spectral lines, scientists can, in theory, weigh the star and measure its radius with extraordinary precision, all from an unimaginable distance. Now try to perform this delicate analysis on a neutron star 12 billion light-years away. The X-ray signal is already faint and stretched by cosmic expansion. Searching for those minuscule absorption notches within that faint signal is an exercise in supreme patience, like trying to read the fine print on a license plate through a foggy telescope from a mile away. Yet the potential reward is a complete physical profile of an object from the early universe, its makeup, its gravity, its size decoded from the whisper-thin skin of gas clinging to its surface. This flawless surface is the launchpad for the universe's most reliable signal. The power of a pulsar's beam originates not from its heat, but from its ferocious magnetic field, which channels radiation into two narrow, opposing jets erupting from its magnetic poles. Crucially, these magnetic poles are almost never aligned with the star's axis of rotation. Picture a lighthouse where the powerful lamp is bolted to the side of the rotating tower, rather than sitting perfectly on top. As the neutron star spins at dizzying speeds, those intense beams of radiation sweep around like cosmic searchlights, carving out vast cones in the darkness of space. Our view from Earth is entirely a matter of geometric luck. If our planet happens to lie within the path of one of those sweeping beams, every time it flashes across our line of sight, our telescopes register a brilliant, fleeting pulse of energy. Then, as the star continues its rotation, the beam points away from us and we see nothing, only for the pulse to return with perfect regularity on the next spin. This is the lighthouse effect, and it transforms an otherwise invisible, city-sized object into a blinking beacon detectable across billions of light-years. The pulses can arrive in any part of the electromagnetic spectrum, from radio waves to visible light to high-energy gamma rays, depending on the pulsar's age and energy. What makes this signal so invaluable for finding the most distant neutron stars is its metronomic precision. Amid the constant, chaotic static of the cosmos, the hiss of interstellar gas, the glow of distant galaxies, the crackle of our own atmosphere, the pulse of a distant pulsar stands out like a perfectly timed drumbeat in a room of random noise. Advanced software algorithms are designed to search for these exact, repeating patterns in years of telescope data. They sift through the cosmic cacophony, looking for that one steady tick that repeats every few milliseconds or seconds with unerring consistency. Finding such a rhythm from a galaxy 12 billion light-years away is an act of profound patience and computational power. It means we have identified a spinning corpse whose lighthouse beam has been flashing with clockwork regularity since not long after the Big Bang, its pulse crossing the expanding universe to finally arrive at our telescopes, a single, clear note in a symphony of silence. That perfect cosmic metronome is not always perfect. Even the most regular pulsar can occasionally stutter, its steady tick interrupted by a tiny, sudden jump in speed. Astronomers call this a glitch. Imagine listening to a clock that has ticked with absolute precision for decades, and then, without warning, it speeds up by a few millionths of a second per day before gradually slowing back to its original rhythm. That is exactly what happens with some pulsars. For a brief moment, the universe's most reliable clock malfunctions. These glitches are not random errors in our instruments. They are real physical events happening on the star itself, and they offer a rare glimpse into the chaotic, alien physics churning within. The leading explanation for these sudden speed-ups involves a dramatic internal struggle. Remember, a neutron star is thought to have a rigid, crystalline crust floating atop a superfluid core. A superfluid is a bizarre state of matter with zero viscosity. It flows without any friction whatsoever. This neutron superfluid in the core is spinning along with the star. Over centuries, as the crust gradually slows down due to its magnetic braking, the frictionless superfluid core can, in theory, spin a little bit faster, lagging behind. It is as if the outer shell of a spinning egg slows down, but the liquid yolk inside keeps whirling at its original pace. This creates a growing differential in rotation speed, a store of pent-up kinetic energy. Then something triggers a transfer. Perhaps a tiny starquake cracks the crust, or the vortices in the superfluid suddenly unpin from the crust's lattice. In an instant, a torrent of angular momentum from the faster spinning superfluid floods into the solid crust. The crust, the part we see pulsing, experiences a sudden tiny speed up. Afterwards, the two components recouple, and the star's spin gradually relaxes back to its pre-glitch slowdown rate. Each glitch is a data point, a direct probe of the interior. The size of the glitch tells us about the amount of superfluid involved. The relaxation time tells us about the viscosity and coupling between the crust and the core. If we could ever detect a glitch from a pulsar in a distant galaxy, it would be a monumental achievement. It would mean we are not just seeing a steady beacon from the early universe, but we are witnessing its internal dynamics in real time, across billions of years. We could ask, did the first neutron stars glitch in the same way as modern ones? Does the behavior of superfluid matter under extreme pressure change over cosmic time? Each microscopic hiccup in that ancient pulse carries answers about the fundamental nature of matter itself. These microscopic hiccups and monumental collisions all converge on a single, profound purpose. Neutron stars, especially the ancient ones we find at cosmic distances, are the universe's ultimate physics laboratories. They are not just objects to catalog, they are instruments for testing the laws of nature under conditions we could never replicate on Earth. Every time we measure a pulsar's spin, weigh a binary partner, or catch the afterglow of a merger, we are conducting a fundamental experiment. Their primary role has been to put Einstein's theory of general relativity through its most extreme trials. The precise orbital decay of binary pulsars, like the famous Hulse-Taylor system, provided the first indirect proof of gravitational waves, a triumph that earned a Nobel Prize. The way a pulsar's signals are delayed as they travel through the warped spacetime of its companion, an effect called the Shapiro delay, offers another razor-sharp test. Each new distant binary system we discover is another chance to ask, does gravity behave exactly as Einstein predicted 12 billion years ago, or are there subtle deviations that only reveal themselves over cosmic time? Beyond gravity, these stars probe the very fabric of matter, the crushing densities inside a neutron star, where a teaspoon of material weighs 1 billion tons, push matter into a state called supernuclear density. Here, the familiar rules of atomic physics break down. We cannot create such conditions in any particle collider, so we must use the neutron star itself as our experiment. By carefully measuring a star's mass and radius, often through the subtle effects of its gravity on light or a companion, astronomers can infer the equation of state of dense matter. This is simply the relationship between pressure and density under these insane conditions. A softer equation of state means matter is more compressible, leading to a smaller star for a given mass. A stiffer one predicts a larger star. Every new measurement, especially from a distant object, helps rule out theoretical models and tells us how matter behaves when squeezed beyond all recognition. This, in turn, reveals the properties of the strong nuclear force, the glue that holds atomic nuclei together, under pressures where it competes directly with gravity itself. The detection of gravitational waves from neutron star mergers has opened a breathtaking new chapter in this research. The ripples in spacetime carry encoded information about the star's masses, spins, and how they deformed each other just before collision. The way they tidally stretch tells us about their internal stiffness. The flash of the kilonova that follows reveals the nuclear alchemy happening in the ejected debris. Each distant neutron star we find, whether it is a solitary pulsar ticking in the void or a pair destined to collide, adds another crucial date, a point to these tests. They are natural gifts placed at strategic distances across space and time, allowing us to run the same physics experiment from different eras of the universe. By studying them, we are not just learning about dead stars, we are interrogating the fundamental rules that govern reality itself, from the force that binds atoms to the geometry of the cosmos. But the physics experiments we run today are just a prelude. Our current telescopes and detectors have only begun to map the faint whispers from these distant corpses. The next decade promises a revolution in our ability to find and understand them. On the horizon are observatories so powerful they will turn the cosmic volume up to levels we can barely conceive. Leading this charge is the Square Kilometre Array, or the SKA. This is not a single dish, but a vast network of thousands of radio antennas spread across South Africa and Australia. When fully operational, its total collecting area will be, as the name suggests, about 1 square kilometer. This makes it phenomenally sensitive, able to detect the faintest radio whispers from the edge of the observable universe. For pulsar hunters, the SKA is a dream machine. Current estimates predict it could discover tens of thousands of new pulsars, effectively tripling the number we know. More importantly, its incredible sensitivity means it will hear pulses that are currently too faint and too redshifted to detect. It will find pulsars in galaxies far beyond our local group, pushing our sample of these cosmic clocks deeper into the universe's past than ever before. Each new distant pulsar will be another precise anchor point in our gravitational wave detection network, and another day, a point for testing fundamental physics across cosmic time. But the revolution is not limited to radio waves. In the realm of high-energy light, next-generation X-ray observatories are on the drawing board. Missions like the European Space Agency's Athena, the Advanced Telescope for High-Energy Astrophysics, will have a mirror with an unprecedented collecting area for X-rays. It will be able to detect the faint thermal glow of isolated, cooling neutron stars at distances previously impossible, allowing us to take the temperature of these ancient embers and peer into their exotic interiors. It will also study the violent accretion flows in distant X-ray binaries with stunning detail, watching how these cosmic vampires feed in real time. And then there are the gravitational wave detectors. The current ground-based network, LIGO, Virgo, and CAGRA, will undergo continuous upgrades to become even more sensitive, but the future truly lies in space. The Laser Interferometer Space Antenna, LISA, is a planned mission that will consist of 3 spacecraft flying in a giant triangle, millions of kilometers apart. Free from the seismic noise of Earth, LISA will be tuned to hear the low-frequency gravitational waves that ground-based detectors cannot, the kind produced by the slow in-spiral of supermassive black hole binaries and, crucially, by the mergers of neutron stars with massive black holes. It might even detect the continuous hum from millions of binary white dwarfs and the ringing of individual neutron stars after a starquake. With these tools, we will not just find more distant neutron stars, we will study them in a multi-messenger symphony, combining their light, their pulses, and their space-time ripples into a complete picture. The most thrilling prospect is that these instruments will inevitably find something we have not predicted. Every time we build a telescope that can see farther or hear more faintly, we discover phenomena that challenge our textbooks. The distant universe, viewed through these new eyes, will likely reveal neutron stars behaving in ways we cannot yet imagine, spinning in patterns we do not expect, or merging with objects we have not yet classified. The 25th fact about the universe's most distant neutron stars is this: their greatest secrets are still waiting for us, hidden in the faint signals that only the telescopes of tomorrow will be able to catch. One of the most explosive mysteries in modern astronomy may have its answer in these dense, spinning corpses. For over a decade, astronomers have been baffled by fleeting blasts of radio energy that erupt with the power of 500 suns in just a thousandth of a second. These are fast radio bursts, or FRB. Their source was a complete enigma, sparking theories from evaporating black holes to alien communication, but the most compelling suspect has emerged: the highly magnetized neutron stars known as magnetars. The connection makes perfect sense. We already know magnetars are capable of sudden, catastrophic releases of energy when their crusts crack and their magnetic fields snap. A massive starquake could, in theory, launch a shock wave through the magnetar's surrounding magnetic environment, accelerating particles that then emit a brilliant, coherent flash of radio waves. Another possibility involves a magnetar interacting with the debris left over from its violent birth. If the neutron star is surrounded by a swirling disk of supernova fallout, or is plowing through a dense cloud of interstellar material, its immense magnetic field could interact with that debris, generating powerful electrical currents that erupt as a radio burst. The evidence is growing stronger. In April 2020, a magnetar within our own Milky Way, named SGR 1935+2154, had a major outburst. For the first time, telescopes caught it emitting a radio burst that looked, for all intents and purposes, like a weaker, galactic version of a cosmological FRB. It was a smoking gun, proving that magnetars are indeed capable of producing these phenomena. Even more telling, many of the repeating FRBs, those that flash from the same spot in the sky over and over, have been traced back to distant star-forming galaxies. These are the very environments where young, massive stars live fast, die young, and leave behind magnetars. The localization of these bursts to such galaxies strongly implicates the activity of newborn, highly magnetized neutron stars. So when we detect a brilliant, milliseconds-long radio flash from a galaxy 12 billion light-years away, we might be witnessing the tantrum of a magnetar from the universe's childhood, its magnetic fury echoing across the ages. A galaxy's history is written not only in its living stars, but in its dead ones. Every single distant neutron star we detect is a final punctuation mark in the life story of a giant. It is the dense, compact signature of a massive star that lived fast, fused elements furiously, and died in a spectacular supernova explosion billions of years ago. But these are not just random tombstones scattered through the cosmos. Their very existence, their numbers, and their locations weave a grand narrative about the universe's formative years. To understand this, think of a forest. If you walk through a young forest, you see mostly saplings and young trees. In an ancient forest, you find towering elders, fallen logs, and a rich layer of decay that nourishes new growth. A galaxy is similar. By counting the number of neutron stars, the stellar corpses, and mapping where they are, astronomers can reconstruct the galaxy's past. A galaxy teeming with neutron stars, especially in its central regions or ancient globular clusters, tells us it experienced intense bursts of star formation long ago. It had a wild youth where countless massive stars were born, lived their short, brilliant lives, and died in rapid succession. The distribution of these corpses reveals where those stellar nurseries once blazed. More profoundly, the types of neutron stars we find act as a fossil record of the types of stars that created them. The prevalence of fast-spinning millisecond pulsars hints at a past rich in binary star systems, where one star fed its corpse companion. The detection of magnetars suggests regions where the most massive, magnetically potent stars once ruled. This census of the dead directly informs the initial mass function, a crucial astrophysical concept that describes the distribution of stellar masses at birth. Were the early universes factories for more heavyweight stars than we see today? Did the first galaxies produce stars in a different proportion? The neutron stars they left behind hold the answer. Each one is a data point in a cosmic demographic study, telling us not just about individual deaths, but about the population, dynamics of stars in the cosmos's first chapters. Their collective legacy is one of transformation. Those ancient supernovae did more than create neutron stars. They blasted newly forged heavy elements, oxygen, carbon, iron, and eventually the gold from mergers, back into interstellar space. This chemically enriched gas became the raw material for the next generation of stars, planets, and ultimately, life. The neutron stars themselves, with their immense gravity, can act as dynamical catalysts, influencing the orbits of other stars in dense clusters or even getting ejected from their host galaxies entirely to wander the intergalactic void. So when our telescopes capture the faint pulse from a neutron star 12 billion light-years away, we are reading a single sentence from a galactic autobiography. That sentence speaks of a giant star's violent end, but also of its generative power, its role in seeding future worlds, and its permanent mark on the evolving structure of its home galaxy. It is a reminder that death in the cosmos is never an end, but a transformation that fuels the next great act of creation. Their faint pulses are echoes from the dawn of creation. As we reach the final fact, we must see these distant neutron stars not merely as extreme physics experiments, but as historians. They are our most direct windows into the early universe, silent witnesses to a time when everything was hotter, denser, and far more violent. When we detect a neutron star 12 billion light-years away, we are not just measuring a spin or a magnetic field, we are receiving a data packet from the cosmic dark ages, a message about the very first generations of stars to ever shine. Those progenitor stars, known as population 3 stars, were unlike anything in our modern galaxy. Theorists believe they were colossal behemoths, composed almost entirely of hydrogen and helium, the pristine elements forged in the Big Bang. They lived fast and died young, and their supernova were likely far more energetic than anything we see today. The neutron stars they left behind carry the imprint of those titans. The spin rate of a pulsar from that era tells us about the angular momentum of those first giants. Its magnetic field hints at the dynamos churning in those primordial furnaces. By collecting enough of these ancient relics, we can begin to reconstruct the demographics of the universe's first stellar population, answering questions we could never approach otherwise. Did those first stars form in isolation or in dense clusters? How massive could they truly become? The answers are locked in the spin and structure of their dense, dead cores. Beyond the stars themselves, these distant beacons illuminate the timeline of cosmic enrichment. The early universe was a simple place, a vast expanse of hydrogen and helium. For complexity to arise, for rocky planets and organic molecules to eventually form, space had to be seeded with heavier elements: carbon, oxygen, iron, and gold. This process, called chemical enrichment, began with the first supernova. Each distant neutron star we find marks the spot where one of those foundational explosions occurred. By mapping their locations and estimating their ages from their spin down, astronomers can chart the rate of supernova in the infant cosmos. Was star death a frequent, chaotic barrage in those first galaxies, or a more sporadic event? The answer dictates how quickly the raw materials for future generations were spread. Furthermore, the very existence of a neutron star confirms that its progenitor was massive enough to undergo a core collapse supernova, which produces elements up to iron. But if we can identify a neutron star that later merged in a kilonova, its ancient flash would signal the early production of the heaviest R-process elements. This means these distant objects allow us to watch, in effect, the universe conducting its first chemistry experiments, forging the elemental diversity that would one day make life possible. Ultimately, every faint tick from the edge of observable time is a crucial piece in the grand puzzle of cosmic evolution. Our universe began in a hot, dense state and has been expanding, cooling, and growing more complex for over 13 billion years. The story of that transformation is written in the life cycles of stars. Distant neutron stars are fossil records of a critical chapter in that story, the epoch when the first massive stars completed their life cycles and began recycling their enriched remains back into the cosmic ecosystem. They connect the primordial fire of the Big Bang to the structured galaxies we see today. Without those first generations of stellar deaths, there would be no elements for planets, no material for future stars like our Sun, and no possibility for observers like us to one day look back and wonder. So when a telescope captures the whisper of a pulsar from a galaxy 12 billion light-years away, it is doing more than adding to a catalog. It is gathering evidence for the greatest story ever told, the story of how a simple, empty universe became a complex, vibrant, and element-rich cosmos, capable of forging not just stars and galaxies, but the very conditions for curiosity itself. From the violent birth in a supernova's heart to the faint, final tick of a cooling ember, the journey through these 25 facts reveals the universe's most distant neutron stars as realms of pure extremity. They are the densest objects we can directly observe, where matter is crushed into a state that defies earthly physics. They spin faster than kitchen blenders and possess magnetic fields of distilled ferocity, capable of cracking their own unimaginably strong crusts. They serve as perfect cosmic clocks, their metronomic pulses allowing us to test gravity across billions of years and listen for the hum of colliding black holes. They are the universe's ultimate alchemists, forging gold and platinum in catastrophic mergers that seed galaxies with the ingredients for future worlds. Above all, they are natural laboratories, conducting physics experiments under pressures and densities we could never replicate, probing the very laws that govern reality itself. Our quest to find them, to capture their faint whispers from the edge of time, pushes our technology to its absolute limits and stretches our theories to the breaking point. It is a testament to human curiosity, a drive to understand not just what lies in the darkness, but how the cosmos transformed from a sea of simple elements into the complex, vibrant, and life-bearing place we call home. Each new discovery, each distant pulse or flash, is a piece of that grand story. So tell us which fact stretched your mind the farthest. Was it the teaspoon of material weighing 1 billion tons, the star spinning 700 times a second, or the ancient collision that forged the gold on your finger? Let us know in the comments below, and if you are hungry for more journeys to the edge of understanding, be sure to subscribe. Our next deep dive into the cosmos is already waiting.